So very good evening again. Welcome to PW Platform Operating System course. So discussion in the earlier class was going on deadlocks, wherein I have covered almost the safety algorithm of Banker's avoidance technique. So today we will complete Banker's algorithm, then followed by the next strategy for dealing with deadlock, that is deadlock detection and recovery. And then that will complete the deadlock chapter. We will take the relevant problems, okay, from previous year questions. So the question is, this is the question that I would like to work out. So this is Banker's avoidance technique. In the last class, I have taken up a problem of Banker's algorithm to work out for 5 processes and a single resource R. But I said we can take a comprehensive problem where we can have more than one resource. We can have more than one resource. Like, take the situation of the system. Let me put some lines here so that you can have clarity of understanding. There are 5 processes. And there are 3 resources. The resources are named as ABC. At time t0, this is the situation at time t0, the 5 processes maximum demand is as follows. Here 753322902222433, and their allocation is as given, max and allocation. So these are available values of ABC right now. So here we would like to find out, is the current state at time t0 safe or unsafe? This is what we want to find. Is the current state at time t0, is it safe or unsafe? First of all, what do we need to do? We need to find the values of need. We need to find the values of need of ABC, of all the 3 processes. We need to find the values of need. Is it not? So here this is process P0, this is process P1, this is process P2, this is process P3, this is process P4. The value of need, as I told in my last class, need is nothing but max minus allocation. So 743 will be the need of process P0. Next, P1. 322 minus 200, 122. P2. 902 minus 302, 600. P3. 222 minus 211, so it becomes 011. And P4, 431. This is my need. We said that in my last class, the system is said to be safe. If and only if the need of all processes can be satisfied with the available resources in some order. If we can satisfy the need of all processes in some order, then we say the system is safe. Otherwise, we say it is unsafe. So let us verify here. At time t0, can we satisfy the need of all the processes or not? Let's see. So I start from P0. 332 is my available, 743 is the need I cannot satisfy. Can I satisfy the need of P1? Yes, sir, we can satisfy. What did I said when the need is satisfied? I have to add the current allocation of the process to the current available. Allocation of P1 is 200. I add 200 to 332. How much does it become? 2 is added here, it becomes 5. 3 plus 0, 2 plus 0, 532. So after completing P1, my new available become 532. How? Adding allocation of P1 to available. Next. With 532, I cannot take the need of P2, but P3. Yes, P3. So completing P3 will improve the available to how much? Let us put it here. So 532 plus 211, it becomes 743. Now with 743, I can take up the need of either P4 or P0 also. Not P0, maybe other process. Sorry, need we have to check here. So P1, P3, right? Here. Now I will take up P4. I can take up P4, I can take up P0, I can take up P2 also. So I will take up P4. Any order you can satisfy. So completing P4 will improve the available to how much? 743 plus P4 002. It becomes 745. With 745 next I can take up P0, improving the available to how much? 7 P0 755. And finally I can take up P2, making the available, as you see here, to how much? P2 is allocation, 302 is added here, 1057. 1057. If you see, the total number of copies of ABC are also 1057. Total copies of ABC are 1057. How do you say that? Very simple. Total allocation is how much? 3 plus 2 plus 2. 3 plus 2 plus 2, 7. And here I have 3. 7 plus 3, 10. 1 plus 1, 2. 2 plus 3, 5. 2 plus 2 plus 1, 5. 5 plus 2, 7. Total. So I got total copies after completing all the processes. After completing all the processes, I got total values as 1057. Therefore, I say system is safe. Okay, so that is the order in which you can satisfy the need of the processes. So therefore, boys and girls, I am saying system at time T0 is safe, means it is ready to operate. So far we have not done any operation. Now the operation will start. Now the scheduling will start. Now the operating system will start scheduling processes. So these processes are there in the ready queue. So we say that the system is safe at time T1. Perhaps at time T1, having found that the system is safe, now the scheduling will start. So I will rub off all this part. That's not needed now. We have proved it that it is safe. Now the operation will start. So when the operation starts, we can, as I said, we can schedule any process. We can schedule any process. For example, imagine the operating system schedule process P1. See here. Operating system process started scheduling P1. What is the demand for P1? Demand is 322. Allocation is 200. Demand is this, and further needs is 122. So let us say P1 running for some time. After running for some time, it makes a new request as 102. It makes a new request as 102. Request of process 1. Available copies of ABC are 332. Requesting is 102. So seemingly looks like we can satisfy, but we will not immediately satisfy. The way this work is like a banking situation. Just like when you approach the bank for withdrawal of cash, the banker will not satisfy the request immediately. It will see whether you have sufficient cash or not, whether you have the proper balance or not, whether the bank has sufficient cash or not. Right? If the bank is in safe state, then only it will grant the request. Otherwise, it won't grant the request. That's why this algorithm is called banker's algorithm. The way it works is exactly like the way banks works. That's why it is called banker's technique. When you produce a check, first it will authenticate whether you have the required person, you are the required person or not. You are authentic user or the account holder or not. You have the balance or not. If the sufficient cash is there or not. If sufficient cash is not there, or even if I have sufficient cash but still there are many customers, I cannot satisfy your bulk request. So therefore it will say you wait, because I don't want to operate my system in unsafe mode. Bank never wants to go into unsafeness. The same way it operates here. To decide whether this request initiated by this process should be granted or not. It is like you have 10 lakhs cash in your account. You are asking 2 lakhs. If you ask me, how sir, how can you ask 2 lakhs? What should I tell? Should I have anything to tell? I don't have anything to tell. I have balance 10 lakh. I can ask anything within 10 lakhs. 2 lakhs I can ask, 1 lakh I can ask, 5 lakhs I can ask, or I can ask 10 lakhs, all 10 lakhs. So that's very simple. So now we have to decide whether this request of 102, should it be granted or not? Right? Should it be granted or not? So how are we going to decide that? So it appears to us we have sufficient cash. I have 332. I have 332. I have sufficient cash. But I won't be granting just like that. The approach which is followed is an a priori approach. A very methodical approach, and that is decided by the main algorithm of banker called resource request algorithm. There are 2 algorithms in banker. Number 1, safety algorithm. Number 2, resource request algorithm. Resource request algorithm is the main algorithm to decide whether the request of any process should be granted or not. So let us write the resource request algorithm here. Please see. I am writing the complete algorithm. So I will say algorithm resource request. Resource request initiated by process I. Let's say the request is request of I. Allocation of the process is allocation of I. Need of the process is need of I. And the available values are this. These are the parameters. First step, when the process has made a request, what is the first step that the deadlock manager banker algorithm has to check? What is the first step? Whether the request of the customer of the process is within the need or not, we have to check. If it is not within the need, it is an illegal request. Illegal. Immediately terminate. Okay, fine. If this is also true, fine. This is also true. Request is within the need. I come to step 2. In step 2, now I will see whether the cashier will say, okay, this fellow has account balance 15 lakh and this fellow is asking 10 lakhs. Then the cashier will see how much cash I have in my account, in my bank. Liquid cash, how much? If you see that liquid cash is 10 lakhs, the liquid cash available is 10 lakhs. And this fellow is also asking 10 lakhs. If I give away all 10 lakhs, I will go into problem. So I have to see whether it is within available or not. So request is less than or equal to available or not, available cash in the bank. Like this fellow is asking 10 lakhs, I have only 5 lakhs, how can I satisfy? Immediately I would say, sorry sir, you wait for some time. Till my available cash improve in the bank. If this is also true, okay, this fellow is asking 10 lakhs, I have 20 lakhs. So it appears as if I can satisfy, but I won't satisfy like that. What I do is, I will make a calculation in my mind. The operating system deadlock manager will make a calculation. Suppose if I satisfy the request of this process now, will I be in a position to satisfy the need of remaining all customers or not, all processes or not? If so, then I say my system is safe. If not, I say system is unsafe. Are you getting my point? If after satisfying the need of this or request of this customer, what will happen to the other processes? Will I be able to meet the requirements of other processes or not, other customers or not? If so, I can satisfy. This fellow is asking 5,000, I have 25 lakhs, immediately I can give 5 lakhs, 5,000. That's the point, right? So here I will write like this in step 3. In step 3 we say, assume to have satisfied request I. We are assuming, we are not really satisfying, assuming. So how do I satisfy? I satisfy from need, from allocation, right, from available. So my current available will get reduced by request available. Allocation of the process will improve by request. The need of the process will get subtracted by request. These are the changes that we are going to make when I am assuming to have satisfied the request. So this will transform the system into a new state. That new state should be safe. So here, for that purpose, I say run safety algorithm. To know whether the resulting state is safe or not. Now I say if the resulting system is safe. If system is safe, then grant request I, else deny request I and block the process. Block process I. Process get blocked saying there, sorry sir, I cannot satisfy. This is a simple core logic of resource request algorithm. Hope you understand. I repeat the steps. Check whether request initiated by the process is within the need. If it is so, I come to check, is it within available? If so, I assume to have satisfied the request. When I am assuming to have satisfied the request, These are the operations which I carry out. And then I check whether after carrying out these operations, is my system safe or not. If it is safe, then I satisfy. If it is unsafe, then I deny. What did I say? Process P1, listen, process P1 made a demand for 322, allocated 200. Using this 200, it ran for some time, and then it asked 102, these are requests. So I want to know, based on resource request algorithm which I have described just now, whether this request of 102 will it be granted or not. So I want you to apply all the steps which I described and ascertain and tell me whether this request of 102 will be granted or not. First point, I am doing step by step. 102 is within the need of process, yes. 102 is within available, yes, because 102 is less than 332. Third step, we are assuming to have satisfied the request. So when I assume, my new available will become 332 minus 102, it become 230. Clear? And then allocation, see this allocation of process P0, I will do like this. Allocation of process P0 will become here from 200, it will change to 200 plus 102, 302. So this will become 302. The need of P1 will change from 122 minus 102, 020. Step ABC have been applied, very good. Now I check whether resulting state, this state with new available, now this is not my available, this is my available. So with this available, can I satisfy the need of all processes? Let us verify step by step. So can I satisfy the need of P0? Here I will check, here. Can I satisfy the need of P0? No, I cannot. Can I satisfy the need of P1? Yes, 020 is less than 230. So I complete P1. So when I complete P1, what will my new available become? So current allocation 302 is added to this, so it becomes 532 after completing P1. Then P2 we cannot, P3 we can satisfy. After completing P3, my new available will become how much? Boys and girls, P3. So P3 allocation of P3 is 211. 211 when I add, it becomes 743. With this I can take up next P4. So when I complete P4, what will my new available become? The allocation of P4, so 002 is added, 745. So with that next I can take up P0, allocation of P0, 010 is added. So what will it become? 755. And then lastly I take up P2. So therefore it becomes 1057. That's all, no rocket science, very simple concept. This is one safe sequence. Means system is safe, therefore request is granted. When request is granted, the changes that we made become permanent, meaning boys and girls, changes will become permanent. That means this will not be 122 now, this will be 020. This will not be 332, it will be 230. So I will rub off this. So my new available will become 230 because request is granted. The cashier has given the cash to the customer. So this will become 302. This will become 020. And system will continue, process will continue because request is granted. I'll take few more problems, please work out. So after some time P1 get preempted. And let's say here I am working out. Boys and girls, please be ready. Now time has become T2. At time T2, operating system decide to schedule process P4. Look at this, process P4. Operating system decide to run P4. P4 demanded 433, allocated 002. Using 002, it will run for some time. After running for some time, it makes a new request as 330. This is the request of process 4. And you have to tell whether this request of process 4 will be granted or not granted. Request is 330, available is 230. How can I grant? How can I satisfy? So immediately I write here not granted. Very good. Now I'll take another example, T3. P0, I run a new process P0. P0 demanded 753, allocated 010, using 010 run for some time, and then it requests 020, 020 is a new request of process P0. Decide and tell me whether this request will be granted in the current circumstances or not. 020 is less than within the available is 230, yes. 020 is less than need of the process, yes. Now we are assuming to have satisfied the request. So when I assume to have satisfied the request, my new available will become 230 minus 020 means it will become 210. It will become 210. Correct? And what will the new need of the process P0 will become? I will write here. It will become 723. And the new allocation of P0 will become 030. I will write it here. 030. These are the changes. I have to see whether this new state is safe or not. So let's verify. Is this state safe or not? So point number 1. We need to verify with this. Can I satisfy 723 from here? No sir, we cannot satisfy. Can I satisfy the need of P1 020 from here? No sir, we cannot satisfy. Can I satisfy the need of P2 210? No sir, we cannot. Can I satisfy? Here people get mistaken. 011 from 210? No sir, we cannot, because this fellow asked for 1 copy of C. I have 0 copies of C. How can I satisfy? Can I satisfy 431? Absolutely no sir, we cannot satisfy. So I cannot satisfy the need of all the processes. So therefore I say system is becoming unsafe. System is becoming unsafe. System is becoming unsafe. And hence we don't satisfy the request. We don't grant the request. System is becoming unsafe. Got it? So deny the request. Request is denied. So what I wanted to tell you from the last point, that T3, P0, is that it appears to us, boys and girls, listen, it appears to us as if we can satisfy, because the request is within the need, the request is within the available cache. But if I satisfy now, in future immediately I may go to unsafe. So that's why I am precautious. I don't want. It is like one customer came in the early morning to the bank, very first hour of the day. The banker has got cash 20 lakhs, and that customer from his account he is asking 15 lakhs. And behind him there is a queue with 100 more customers. Available cash 20 lakhs, and this fellow is asking 15 lakhs. His account he is having 25 lakhs, let us say. So it is within his balance, and I have sufficient cash 20, he is asking 15. But I play a safe game here. Cashier, play a safe game. Because if we give away 15 lakhs cash from available 20 cash, then what will happen to the remaining customers? Right? They will shout and make a cry. The moment the cashier say after some time that there is no cash in the bank, the remaining customers will not keep quiet. The banking officials will have to listen to the nice music of the remaining customers. They will not keep quiet. So this bank will become unsafe. Right? So we don't want to operate the bank in unsafeness. So what will the banker tell? Banker will not say, sir, I will not give you the cash. Banker will say that, sir, you have to wait for some time till my available cash improve, and you come after 3 hours, you come after 2 hours, I will make arrangement for your cash and hand over to you. Why? Because I don't have sufficient cash. Many a times it happens to me also. For simple 2-3 lakhs withdrawal, when I go to the bank, they say, sir, sorry sir, right now there is no cash, you come after some time. This is as per rule, but boys and girls, this is as per rule. As per banking rule, this is the situation. Okay? Bank has got the right to deny your request for a while. Why? Because we want to operate the system in safe mode. That is the point. So that is the same situation here. Fine. So this is the problem of banker's algorithm. Which of the following is not, he is saying, look at that, is not a valid deadlock prevention scheme. Release all resources before requesting the resource, this is a valid. Number all resources uniquely, this is valid. For circular wait. Never request a resource after releasing any resource is not a valid, this is valid. Got it? So option C is correct. Next question. Which of the following is not again true, not true, of deadlock prevention and deadlock avoidance together? In deadlock prevention, the request for resources is always granted if the resulting state is safe. First option, is it true or false? First option is false, because in deadlock prevention, we never talk about safe or unsafe. In deadlock prevention, there is no concept like safe. That's a mistake. So therefore, it is false. In deadlock avoidance, the request for resource is always granted if the resulting state is safe. This is true. Deadlock avoidance is less restrictive than deadlock prevention. This is true. Deadlock avoidance requires knowledge of resource requirements a priori beforehand. I told yesterday, true. So therefore, the correct answer is A. Not true, he's saying. Got it? So questions like this are typical and important, and that is why I say to solve questions, your concept should be clear. So such questions, if you see that, no, if I solve test series, if I work out this problem, that problem, it will not help. Foundations are required. So if you make your foundations clear, such questions can become easy. The point is very simple. In deadlock prevention, the request for resources is always granted if the resulting state is safe. Where is the question of state? There is a question. Safe and unsafe is an avoidance algorithm. Deadlock avoidance is less restrictive because in deadlock prevention you have lot of restrictions. On every condition you have lot of restrictions. In deadlock avoidance there is only one restriction, that every process will have to ask for maximum demand for resources. That is the only one. That's why this is true. That's what I said. That is a concept. You need to visualize. In deadlock prevention, so many restrictions are there for the process to prevent deadlock. Like you request all the resources beforehand, you release all the resources before requesting, you number all the resources uniquely. These are restrictions. These are restrictions. An operating system implements a policy that requires a process to release all resources before making a request for another resource. So that means this policy is for deadlock prevention. This policy is for deadlock prevention. Which condition? Hold and wait. Hold and wait. So what did we say? It will definitely prevent deadlock. But starvation can happen, I already discussed. So therefore, starvation can occur, but deadlock cannot occur. Very correct. Option B is correct. So let's take up the last strategy, the fourth one. In sequence, deadlock detection and recovery. Deadlock detection and recovery. So as I told in my last class yesterday, that when I adopt this strategy, when I go for this strategy, this will allow the system to go into deadlock. Deadlock occurs. Deadlock occurs. Deadlock prevention, deadlock do not occur. Deadlock avoidance, deadlock do not occur. Deadlock detection and recovery, deadlock occurs. Correct? Deadlock ignorance, deadlock occurs. So that's why we say detection and recovery. I would like to emphasize here and tell you that there are two things here. One is deadlock detection and the other is recovery. There are two parts. So first we'll talk about detection. Right? So in detection, there are two algorithms. There are two algorithms in detection. One is for the case of single instance resource. Single instance resource. That means when my system has got resources of single instance type, and the other is multi-instance resource. Multi-instance resource. Single instance resource and multi-instance resource. Both are very clear. That means how am I going to detect the deadlock when my system has got single instance resource and when my system has got multi-instance resource? But before I take up that, I have one fundamental question to ask. The question is, when I'm using deadlock detection and recovery in my operating system, the basic fundamental question that arises is, when should the operating system deadlock manager apply, activate deadlock detection test? I say that deadlock detection is a test. It's a test. Test for what? Test to know whether deadlock is there or not. It's a test. So I'm asking you, when should the operating system deadlock manager should activate, apply, invoke the deadlock detection test? This question of asking when should we apply deadlock detection test is just like, listen to me carefully, is just like asking a person, asking any person, when do you go to doctor? It is as good as asking a person, When do you go to a doctor? The person will not say, sir, to be on safe side, I visit the doctor daily, morning and evening. No, person will not say like that. Is it not? The person will say, sir, I will approach the doctor, I will go to doctor when I am not feeling well. When I am not feeling well. Correct? I am having this pain, that pain, then I go to doctor. I will tell my story to doctor, doctor will listen to my story, and based on his experience, he will come to a conclusion in a mind that this person may be suffering from this problem, that problem, something. To ascertain or reconfirm his analysis, what will the doctor do? Doctor will write a prescription and say that, please carry out this test, blood test, this test, that test. So he has understood the symptoms, and based on the symptom to confirm, reconfirm, the doctor say, you carry out these tests and come to me with the report. Listen to me. Symptoms test. Activation of test is based on symptoms. I am having this pain, that pain. The customer or the client or the patient will say something based on that, doctor analyze something, make a guess, and to reconfirm the guess, he will activate the test. So based on the symptoms. So like that, what are those symptoms in the system for which the operating system, deadlock manager, like a doctor, activate the test. In the literature, even though it is not there, but my understanding say, based on my experience, that deadlock detection and recovery is just like doctor's algorithm. I say it is like that, doctors. It is the way it works is just like doctors. You have a symptom, you approach the doctor, doctor will subject the patient to the test. Result of the test may be positive or negative. And if it is positive, doctor will initiate recovery. If it is negative, doctor will say nothing to worry about, enjoy life. Same way it happens here. So here we need to understand, to my question, when should the deadlock manager as a doctor activate the test? When the system is not well, when there are symptoms. What are the symptoms? The symptoms are underutilization of CPU. Underutilization of CPU. If the CPU utilization drastically comes down, that's a symptom that there may be a deadlock. We don't know, but still. Majority of the processes are blocked. Majority, I mean greater than 50%. Majority of processes are blocked. Why? Because when deadlock happen, processes get blocked. The majority of processes are blocked. That's a symptom that there may be a deadlock. So boys and girls, these are the two major symptoms for the processes to get blocked, and utilization of CPU drastically coming down is a clear indication that the system might be in deadlock. So we activate the test. So what are the tests? As I said, there are two tests. Number one here, number two here. Single instance resource, multi-instance resource. So here I am saying deadlock detection for single instance resource. It is based on a concept called wait for graph, which I am going to discuss. And multi-instance resource, it is just like based on safety approach, which we have seen. So both the approaches we'll talk about, right? So this is for the first one. Listen to me. The first deadlock detection test. The first deadlock detection test is for the case for single instance resource. Single instance resource. When the system has got resources of single instance type. Resources have got single instance. All resources are single instance. So if you study this, there are 5 processes, boys and girls, P1, P2, P3, P4, P5, 5 processes. 5 resources. Here I would like to tell you that, all these resources are single instance. You can mark if you want like this, single instance. All these are single instance. One copy. If there are multiple dots, then only multi-instance. What is the state of P1, P2, P3, P4, P5? Let's analyze. P1 is requesting for a copy of R1, which is right now with P2. P1 is allocated a copy of R2. P4 is requesting R2, allocate a copy of R5, and P2 requesting this, P3 requesting this, like this. Now based on the previous discussion, please tell me what are the current states of the processes at time t. This is the current time t. current time t, what are the current states of the processes. Out of 5 processes, how many processes are blocked? Yes, except P5 or are blocked. 4 are blocked. P1, P2, P3, P4. So this is a symptom. This is a symptom. So on this symptom, we are going to, on the occurrence of this symptom, we are going to apply deadlock detection test. How is that done? By deriving a subgraph or a metagraph from here called wait for graph. We are deriving another graph from here called wait for graph. Wait for graph. The characteristic of this wait for graph is that it will have only processes as vertices. Look at that. The wait for graph derived from the original resource allocation graph will have the characteristic that it will have only processes as vertices. Look at that. P1, P2, P3, P4, P5. So I have took the structure. See here on board how we are deriving this. P1 is waiting on P2 for resource R1. Again check. P1 is waiting for R1, which is right now in with V2. So I can say for sure that by removing this, I can remove this and put a direct wait for edge like this, P1 to P2. That is called wait for edge. So I say P1 is waiting on P2 for resource R1. So collapse this, remove this and put a direct wait for edge. Wait for. P2 waits on P5. P2 waits on P3. P2 waits on P4. P3 waits on P4. Look at this. P4 waits on P1. P5 waits on no one. This is wait for graph. On this wait for graph, boys and girls, on this wait for graph, you run cycle detection algorithm to detect the presence of a cycle. And if it report like breadth first search or depth first search, you can apply, that will report the presence of a cycle. Do we have a cycle here? Yes sir, we have a cycle. P1, P2, P3, P4, P1. We have a cycle involving between these 4 processes. The cycle is P1, P2, P3, P4, P1. The largest cycle indicate the number of block processes, number of deadlock processes. So cycle in a resource allocation graph having single instances is a necessary and sufficient condition, therefore deadlock. Means these 4 processes are in deadlock. P5 is not in deadlock. P5 is not in deadlock. So think that, assume that, or remember this point, whenever deadlock happens in the system, it is not necessary that all processes of the system should be in deadlock, not necessary. Few of them, a subset of them, like in this case. P1 to P4 are in deadlock, P5 is not in deadlock. So the output of this algorithm is deadlock processes. This is the output. So these deadlock processes will go as input recovery module to recover the system. How? We shall see shortly. But before studying recovery, we need to understand multi-instance resource. This is star algorithm. How to detect deadlock? In the case when resources are multi-instance, when I have resources with multi-instance. So let us see that. So hope this point is clear. It's a very simple algorithm. Step 1, derive wait for graph. Step 2, run cycle detection algorithm. If there is a cycle, determine the processes in the cycle. Those processes are in deadlock. That's it. The output is deadlock processes. Those are victims. Those victims will go as input to recovery. Finish. Then we study deadlock detection with multi-instance. So this is the algorithm. This is the algorithm for multi-instance type. This is the algorithm for multi-instance type. So how do we detect deadlock with multiple instances? So let's see here. So let me write here. Deadlock detection with multi-instance resource. When the resources have multiple copies, how do we detect? I would like to only tell you that the approach which is followed here is just like Banker's algorithm. So that's why the data structures used here are very, very simple. So let me talk about the data structures first. So boys and girls, see here. The data structures are as follows. We have processes, allocation matrix, maximum matrix. No, this I should not have maximum. Allocation, and this is request. This is called request matrix. and then available. Here we will not have maximum, here we will not have need, only current allocation to the process and what is the request, that's it. These are the data structures for deadlock detection with multi-instance. What is my current allocation and current request, just like previous diagram you observe, current allocation and current request, that's it, the same. There is nothing like need or maximum here. So what is my current allocation and is there any request and what is the availability? So these are situation at time t0. At the outset I ask my first question. My first question is always like deadlock detection. When I am working, I will have to ascertain about the symptom. Do we have any symptom? So for that I should check what are the current states of the processes. How many processes are blocked? Here the request, look at the request. Request of P0 is 000, so not blocked. 202 blocked. Why? Because I have available 000. This is not blocked, this is blocked, this is blocked. So how many are blocked? How many are blocked? 3 are blocked. 3 processes are blocked. Who are the 3 processes? P1, P3 and P4. P1, P3 and P4 are blocked. Out of 5, 3 are blocked. Majority are blocked. That's a symptom. So therefore we activate deadlock detection test. The test is very simple. The test is very simple. It works like safety algorithm. We say only this thing. At any point of time t, the system is said to be either safe or deadlock. Like in Banker's algorithm, it is safe or unsafe. But in deadlock detection, it is safe or deadlock. That's the difference. Again I repeat. In avoidance, Banker's algorithm, at any point of time, the system is said to be either safe or unsafe. Safe or unsafe. Safe means no deadlock. Unsafe is like a danger. But in deadlock detection, at any time, the system is said to be either safe, if not deadlock. There is no concept of unsafeness in deadlock detection. So when do we say system is safe? Very simple. System is said to be safe, that is no deadlock, if and only if the request of all processes can be satisfied with available resources, just like safety algorithm. As we work in Banker's algorithm, just like that. There we have to check with respect to need, here we have to check with respect to request. So if the request of all processes can be satisfied with the available resources in some order, system is safe. Otherwise, it is deadlock. And those processes whose request cannot be met, those are in deadlock. That's it. So let's verify here at time t0. Is our system safe or deadlock? Come on. So can I satisfy the need request of P0? Yes sir, I can satisfy. Because P0 is saying 000. So if I complete P0 like safety algorithm, what will my new available become? New available become 010. Add allocation to this. With this I cannot satisfy the request of P1, but P2, yes, P2 we can satisfy. After completing P2, what will my new available become? P2. 303 is added to this, 313. Now with that I can next take up P3. So my new available will become, add P3, 211, 524. And with that next I will take up P4. It will become how much? It will become P4. P4 allocation 002 is added to this, 526. Is it not? And then finally I can take up P1. P1 is 200726. I get my total copies back. So system is safe, means no deadlock. So what I'm trying to say, even though there are 3 processes blocked, majority are blocked, but still there is no deadlock. There is no deadlock, system is safe. So now when system is safe, so I can remove this. And when I say my system is safe, I can continue my operation. So at time t1, listen to me, interesting. At time t1, I say that there is no problem. Like doctor is saying, result of test is negative, nothing to worry about, you can continue life, enjoy life. Time t1, the operating system decide to schedule the processes. Among those which are runnable processes. Who are runnable? Those processes which are not blocked are runnable. Who are not blocked? P0 is not blocked, P2 is not blocked. So I can run any of these two. So let us say the operating system decide to run P2. Let us say the operating system decide to run P2. P2 is allocated 303, right? So using that allocation, P2 runs for some time, and like earlier occasion, now P2 comes up with a new request. It say that now I want 001. Listen to this. This is a new request of process P2. I have available 000. So the request entry of 000 will change to 001 new request. The moment this make request, it will get blocked. Why? Because I don't have any free copies. It get blocked. Earlier 3 processes were blocked. Now a new 4th process got blocked. Now we get a doubt. Do we have a deadlock now? Again apply the same thing. Recheck whether system is safe or deadlock. Recheck. Apply safety algorithm again. So here we will test. Boys and girls, please see. I start like earlier occasion P0. I can complete P0. Yes sir, you can complete. So what will my new available become? 010. Now look, with 010, can I satisfy the request of 202? No sir. Can I satisfy the request of 001? No sir. Because this fellow want 1 copy, have 0 copies. Can I satisfy the request of 100 from here? No sir. Can I satisfy 002? No, I cannot. So now I say there is a deadlock. This is idea. Earlier there was no deadlock. Now there is a deadlock. There is a deadlock. So who are the processes who are in deadlock? P1 to P4 are in deadlock. P0 is not in deadlock. P0 is not in deadlock. P1 to P4 are in deadlock. So this is the output of deadlock detection. Deadlock processes, victim processes. So these deadlock processes will go as input to recovery strategy, recovery module. So output of both the algorithms is deadlock processes, processes that are involved in deadlock that will go as input to recovery. So question is, how do we recover the system from deadlock? How do we recover the system from deadlock? So let's see recovery. I'll come to this level. Look at this recovery. Just glance through this diagram for recovery. Recovery from deadlock, approach 1, approach 2. Approach 1 is processes, dealing with processes. Approach 2 is dealing with resources. So here deadlock processes, for example, from previous data is P1 to P4. These are the deadlock processes. First approach is this, second approach is this, dealing with the first processes. Abort means kill. Kill one process at a time until the elimination of deadlock cycle. So what this strategy says is, when 4 processes are involved in deadlock, you start killing one by one. Take P1, kill it. Then check, is deadlock overcome? If no, take another victim, kill it one by one till deadlock cycle is broken. This is one approach. The advantage of this approach is, the advantage of killing one at a time is, maybe you can save few processes. But the drawback is you have to apply deadlock detection cycle again and again till deadlock cycle is overcome. Kill one at a time. This strategy is abort all, or you say kill all, all the deadlock process P1 to P4. Advantage is there is no need to apply deadlock detection test. Deadlock is overcome. Kill all of them, P1 to P4. The drawback is some important priority processes will get killed. Imagine P1, one process P1 who was in deadlock, it completed 95% of its execution. If you kill this process, you have to restart the process again. Means the process has consumed 95% of its execution and you are killing it. It was about to complete, you are killing it. You have to restart the process again. So that means 95% of the time the process that it has used the resources, all that is going waste. All that is going waste. So that is a drawback of killing all. There is the advantage of killing one at a time. You can save such processes in killing one at a time. That is the comparison. That's the comparison. Resources. The other approach is operating system will kill. Recovery system. Yes, with commands like kill command, kill is a command for user level. Operating system will have its own approach of killing. So in this regard, students, my dear students, I used to say that the approach which is followed by recovery module, is like different types of doctors. We have doctors like physicians. You have doctors like surgeons. Is it not? In allopathy. Suppose one person goes to one doctor who is a surgeon, they say that no, there is nothing doing, you have to go for a surgery. He recommends surgery directly. That fellow will get afraid. Then his friends and family members say we should take another opinion. And then they say we'll approach another doctor who is a physician. So they approach physician and consult. Physician say that okay, surgery, let us keep it last option. First you take 15 days medication, maybe things will improve. Then we'll see the test again. Then again we will increase. So last option we'll see surgery. This is just like this approach. Kill one at a time is like physicians. Kill all is like surgeons. They say that remove the victim, finish, problem will be overcome. Surgery, perform surgery. So these are like physicians, these are like surgeons. The last approach for dealing with deadlock, which works on resources, is called, they are basically like what kind of doctor? These are like the homeopathy. Or maybe you can say Ayurvedic. They don't believe in killing at all, they don't believe in side effects, as you know the medicines, but it will take a long time. So therefore we say basically applying the deadlock recovery on resources means you apply resource preemption. Because we know the problem of deadlock happens due to lack of resources. So therefore this policy believe in resource preemption with rollback. Meaning I will explain by a diagram. Let us say there are two processes, Pi and Pj. Let us say there are two processes, Pi and Pj. Pi is holding the following resources, some name we'll put, resources A, B, K, L, M, and this fellow is holding the resources like this, B, P, BP, R, Q, T, something like that. Now this got involved in deadlock. This is timeline and these are resources. At this time this resource got allocated like that. Now listen, boys and girls. When I was killing the process, I was taking away all these resources and restarting the process again from beginning. But now with the rollback, the concept is I take away the latest resource held by the process, say M, I take away T and roll back the execution to this state. As you studied in databases, the concept of rolling back the transaction. So same way, I will roll back the state of the process to the time or a place where it acquired the resource. Roll back. So I roll back M, I roll back T, I roll back the state to here. And then apply detection again, because I got some resources, apply detection again. If cycle is overcome, deadlock is overcome, be happy and continue. No, cycle still exists, deadlock still exists, continue rollback. Take away L, take away Q and roll back and continue this. Take 15 days medicine, take the test. Again take 15 days medicine, take the test. It is like that. And see the improvement. If there is no improvement, then last step. If there is improvement, continue. There is a meaning. So that's why I say the working of deadlock detection strategy is just like doctors, different types of doctor strategy. So therefore we say these are the two approaches for dealing with deadlock. One is aborting the process, the other is resource preemption with rollback. Rollback of course is an overhead, is a costly operation as you study in databases also. So but the common drawback of both the strategies, the common drawback of both killing the processes or resource preemption, the common problem of both is starvation. Both will lead to the problem of starvation. So in deadlock detection and recovery also we can have starvation, because if a process is repeatedly getting preempted of its resources, or if a process is repeatedly getting involved in deadlock and getting killed, then such processes will starve to complete. So that's why starvation can happen with deadlock detection and recovery. So I hope, so before I start my discussion with problems and numericals, I would just summarize my discussion with regard to deadlock handling. We said we have studied three strategies: prevention, avoidance, third, detection and recovery, fourth, ignorance. Summarizing discussion now. on the strategies of dealing with deadlock. Please observe. In my last class, I said these two is one type of strategy, this is another type of strategy. The fundamental difference between type 1 and type 2 strategy, I said in my last class, when I apply either this or this, deadlock do not occur. Deadlock not at all occurs. When I apply type 2 strategy, deadlock happens. That's the fundamental difference I told, if you remember. But now at the end of the discussion, I will finally say that these two is one class of strategy, C1. Detection and recovery is class 2 type of approach. This third type, C1, C2, C3. Based on the keywords, based on the approaches I discussed, I can say that I have broadly 3 classes of strategies. It is these 3 classes of strategies is just like 3 classes of people of this world, W-O-R-L-D world. We can say that in this world, people are classified into 3 types, exactly like this. First class C1, they say preventive and avoidance. They are like top class, not in terms of finance, not in terms of their economical background, but in terms of their attitude towards life, class 1. They always believe in prevention is better than cure. Why should we approach the doctor? They are of the opinion that basically health is wealth. Therefore, they take morning walk, evening walk, take 30 calories, 45 proteins per day, something like that, measurable diet. Why should we fall ill? Right? That is their approach. Be always a very disciplined life, class 1. Prevention, avoidance. Second class of people, C2, detection and recovery, they have a different attitude towards life. They believe that they have a different belief system. They believe that ultimately we have come to this planet Earth for a limited period of time. Maybe 60 years average life, 70 years. And by the time we are on our toes, on our legs, it is almost 25 to 30 years. So hardly we have got 20 years to enjoy. Let us enjoy life. They are not particular about health and habits. They are not particular about the hygiene. They say enjoy life. Because we have got super specialty hospitals, well qualified doctors. So they eat whatever they want, they do whatever they like, right? No discipline. Lifestyle, whatever they like, they do. But the moment they feel something wrong, immediately approach the doctor, consult and try to recover. So boys and girls, I would say this class of people is just like proactive. Class 2 is like reactive. They react. At least this is good. They react to the situation. Not feeling well, approach the doctor and get corrected. Last category, C3, is ignorance. Some people you will find in this world of this type, ignorant. Neither they are proactive, nor they react. So even if you tell them, for example, even if you tell them, brother, you're not feeling well, why don't you go and approach the doctor? They say, oh, casual, this is viral fever. Even if you go to doctor, nothing would happen, right? They will tell all stories. This viral fever, it will take 2-3 days and then automatically it will vanish. They say like this, they give argument or justification like this. Sometimes, yes, fever or whatever problem is there, it will vanish automatically. Other time the person vanish. Ignorance. That is a risk. Correct? So that is ignorant strategy. So I would say this is like no active or inactive. So choice is yours, which active you want to become and act accordingly and take up your life, take up your career. Proactive or reactive or inactive. Okay? So this is the summarized discussion with regard to the understanding of different strategies with dealing with deadlocks. Now, we'll take up the discussion on the problem. So I will take up the first problem. A computer has 6 tape drives. Tape drive is a resource. Tape drive is a resource. I will call it as R. So how many copies of R are available? 6 copies. With n processes competing for them, each process may need 2 drives. Each process need 2 drives. Every process Pi need 2 copies of R to finish its execution. What is the maximum value of n for the system to be deadlock free? What is the maximum value of n? What is the maximum value of n for the system to be deadlock free? So for answering that question, listen to me boys and girls, for answering that question, I will ask another question in this. I will ask another question. What is the minimum value of n? Listen to this. What is the minimum value of n for deadlock to happen? Suppose if I have one process, can a deadlock happen? No, I have 6 copies, one process. Each process need 2 copies of our deadlock, never happen. 2 processes, can deadlock happen? No sir, it can never happen. 3 processes, can it happen? No sir, it can never happen. Now people get confused here. With 4 processes, can a deadlock happen? They think that yes, it can happen. We say no, it does not happen. Why? Because even if you give 1 copy here, 1 copy here, 1 copy here, 1 copy here, I have still how many copies left over? 2 copies. 1 copy can be given to this, 1 copy can be given to this. These are of course blocked, but these are not blocked. They got to full copies. So after some time they will release the resources. When they release, that can be given to others. Dining philosopher. In dining philosopher, if I have 4 philosophers and 6 forks, how can deadlock happen? Deadlock can never happen. I hope you got it now. You got it now, right? So with 4 processes, deadlock does not happen. So here I write P1 no deadlock, P2 no deadlock, P3 no deadlock, P4 no deadlock, P5 also no deadlock. Even if I have 5 processes, no deadlock. Deadlock can never happen. But if I have 6 processes, yes, now deadlock can happen. So deadlocks start happening from 6 processes. 6 philosophers, 6 folks, deadlock can happen. 6 philosophers, 6 folks. When will it happen? When in chance, by chance, if everybody get 1, this is deadlock. This is deadlock. So deadlock starts happening from 6. With 7 it will happen, 8 it will happen. So maximum is infinite, minimum is 6 to deadlock. So maximum for deadlock free, maximum value of n for deadlock free operation. Deadlock should never happen. Never happen. What is the maximum? 1 never happens, 2 never happen, 3 never happen, 4 never happen, 5 never happens. The answer is 5. So this is a min-max problem. This is a min-max problem. Dining philosopher, you remember, you will never go wrong. Next question. No deadlock will ever arise mean deadlock free. So how many processes are there? 3 processes. So here processes are given P1, P2, P3. Each process need 2 copies of R again. Check it. Given. Each process need 2 copies of R. So for a deadlock to happen, everybody feels short by 1. Means maximum for a deadlock to happen is 3 copies. Dining philosopher. So if you don't want deadlock, have 1 additional fork plus 1. Plus 1. So therefore, answer is 4. As simple as that. 3 philosophers, 4 forks, deadlock never happen. The minimum number of units for causing deadlock free operation is 4. So next question. I have 6 tape drives, these resource R. So R has 6 copies. Right? Each process Pi now given to be 3 copies of R. Look at this. Each process needs 3 copies of R. What is the maximum number of processes for deadlock free operation? Maximum number of processes. So I do dining philosopher again. P1, if I have only 1 process, boys and girls, if I have only 1 process, can deadlock happen? No sir, it cannot happen. Go for 2 processes, can deadlock happen? No sir, it cannot happen, because if I give 3 copies to both, no deadlock. Sir, is deadlock possible with 3 processes? Come on. 3 processes are there. Every process need 3 copies of R. Can deadlock happen or not? Yes, deadlock can happen. Can happen. I am not saying will always happen. Can happen. Sir, when will it happen? When everybody get 2 copies. When everybody get 2 copies. This is deadlock. Everybody is falling short by 1. Everybody is falling short by 1. This is deadlock, boys and girls. Look at this. This is deadlock. This is deadlock. So deadlock is starting from 3. So if you don't want a deadlock, I should have maximum n is equal to 2 processes. That's it. So that's a typical question. Answer is A. Answer is A. I will tell you, this question is MSQ. So boys and girls, here we say consider a system having m processes, m resources of the same type. These resources are shared by 3 processes A, B, C. So we have process A, B, C. The maximum demand of each process for the resource R is given as 3, 4 and 6. 3, 4 and 6. So boys and girls, here I would like to tell you the condition for deadlock to happen. I said in my discussion that deadlock will happen. For deadlock to happen, right? How many resources everybody should get against the maximum demand falling short by 1, against the demand maximum falling short. That means this fellow want 3, I have 2, deadlock will happen. This fellow want 4, I have 3, deadlock will happen maximum. This fellow wants 6, I have 5. This is the maximum condition for deadlock to happen. Maximum condition for deadlock. What is that count? 5 plus 3, 8, 10. If you don't want, if you say no deadlock, then minimum should be plus 1. That is 10 plus 1. This is minimum. Anything greater than 11, no deadlock. Very obvious. I cannot have a better explanation than this. Minimum is 11 and greater than 11, deadlock never happens naturally. Is it not? So here, if I would have asked you the question what is minimum, answer would have been 11. But he is not asking minimum. He is saying for what values of m deadlock will not occur. Deadlock definitely occur with 7, 9, 10. 13 and 15 it does not occur. Therefore, the answer is D and E, MSQ. So continue in the next class. Take care.